So in this lecture, we're going to talk more about the Canter set. So picking up from last time, recall that every point of the Canter set is a limit point of the Canter set. All right, so last time we showed that every point was a limit point of the set of endpoints of the closed intervals that we use to construct the Canter set. And those closed intervals, those endpoints are in the Canter set themselves. So in fact, every point of the Canter set is a limit point of a countable subset of the Canter set. So another way to say that every point of a set is a limit point of that set is to say that the set has no isolated points. So an isolated point of a set is a point in the set where you can put an open ball around it that contains only that point in the set. So generally, if you have a set and you look at a point in that set, it's either the case that every ball around that point contains a point other than it in the set, or there's some ball that contains no points in the set other than the point itself. Okay, so every element of a set is either a limit point of that set or an isolated point. So to say that everything in the Canter set is a limit point is exactly to say it has no isolated points. And so there's a kind of special terminology for certain types of sets that have no isolated points. So that leads us to our definition here. A subset of Rn, so in general we'll work in Rn, is called perfect if it's a closed set, okay, as we know the Canter set is, and has no isolated points. Okay, so this recall here is basically just, sort of implies immediately that the Canter set is a perfect set, once we recall that we talked about last time that the Canter set is a closed set. So other examples besides the Canter set, which is by far the most interesting example of a perfect set we have. More mundane examples would be Rn itself. Right? Obviously, Rn is a closed set, and it has no isolated points for obvious reasons. And then closed balls and closed cubes in Rn also. So a closed cube in Rn is just a product of closed intervals. And so you take n closed intervals in R and just product them together. That's a closed set, and will have no isolated points, and closed balls similarly. Okay, so the first theorem, so one of the main theorems that we're going to prove today, is the following. So a non-empty perfect set in Rn is uncountable. Okay, so this will establish the uncountability of the Canter set as we discussed in the previous lecture. So it also will imply the uncountability of any one of these other sets as well. So this is an even more general argument that will imply that Rn is uncountable. So here's the proof. So the basic idea of the proof is, well, if this theorem generalizes the uncountability of Rn, so it implies the uncountability of R in particular, maybe for the proof of this theorem, we should go back to our theorem, to how we proved the uncountability of R and see if we can generalize the proof of that theorem. So the basic idea is to generalize the proof of the uncountability of R and it's not the diagonalization argument that we originally used. It's the actually somewhat more rigorous argument using the nested interval property. So the basic idea is to generalize the proof of the uncountability of R using the nested interval property. So let E denote our non-empty perfect set. So it's easy to see that any finite set has to consist of isolated points. So any finite set in Rn must consist of isolated points. So that can be a little exercise for you. Maybe I'll throw that on a homework. So E must be infinite. Right, E is perfect, so it has no isolated points. So it's either countable or uncountable. Okay, so we'll suppose the latter and we'll get some contradiction. So suppose the former and get some contradiction. So suppose the former, that is E is x1, x2, x3, etc. Okay, so the strategy of the proof is this, and this is the generalization of the strategy of proving the uncountability of R using the nested interval property. Okay, so I'm basically recapitulating that strategy to remind you of how we did that. So the idea is the strategy is to do the following, is to find, or I guess I'll say to construct closed balls of finite radius, of positive radius, let's say dn. So closed balls of positive radius, we'll call them dn. So we have the sequence of closed balls. Let me be more clear about that. Say dn, these are the closed balls, such that so they're going to be nested. So dn contains dn plus 1. Xn is not in dn, and dn intersect the set E is not empty. So the idea here is, instead of the nested interval property, we're going to use the fact that nested compact sets. So we have nested compact sets which are non-empty, then the intersection has to be non-empty. So what we have here is these are going to be our nested compact sets. Right? So if the balls are nested, then dn intersect E, those sets are going to be nested. And they'll be compact because dn is bounded, right? Just a bounded closed ball, and E is a closed set. So these are both closed sets. Their intersection is closed. It's bounded, and they're going to be nested. This dn intersect E. Call this K sub n. All those are going to be compact sets which are nested, and they're non-empty, right? Because by this condition. So then their intersection is going to be contained in the set E. Right, so we'll have a non-empty intersection contained in E, except the problem is we're constructing these such that xn is not in dn. Okay, so by explicit construction, xn cannot be in kn, and therefore it cannot be in the intersection of all of the k's. So this intersection is a subset of E, which is non-empty, but also none of the xn's can be in it. And since we've enumerated all of the elements of E, right, they're all here, that's a contradiction. So explicitly, xn's are not going to be on the intersection, but the intersection has to be non-empty. So that's going to be the contradiction there. So let me just write that out. So letting or let's say, provided we can do this, setting Kn to be equal to Dn intersect E, we see that the Kn that is a collection of non-empty nested compact sets. So therefore, K, which is defined to be the intersection of all of these Kn's, is not empty. And we can also say, and K is a subset of E, right? So each of the Kn's is a subset of E by definition. So K will be a subset of E. However, Xn is not an element of Kn. So Xn is not an element of K for each n. So this yields the contradiction that K is a non-empty subset of E, but no element of E is contained in it, but no element Xn of E is contained in it. Okay, so therefore it suffices to complete the proof. So to complete the proof, we just need to construct the dn's as we discussed. So we just need to construct the closed disks dn as above. Okay, so the first step is easy. So the main thing about these disks is that they need to avoid, so dn has to avoid xn. So if we imagine we have x1 here and x2 here, we want to create some disk that avoids x1. So what we can do is just simply make a disk around x2 of, let's say, radius length of x minus x2, right? So the distance between x and x2, we'll cut that in half, and that'll be the radius of our first disk. So to start, to begin, set d1 equal to the closed ball of radius x1 minus x2 over 2 around x2. So clearly we have that x1 is not in D1. Okay, if x1 were in D1, then x1 would be within, within half of the distance of the distance between x1 and x2, and that makes no sense. And let's also remind ourselves of what the conditions are. So we need these balls to be nested for them to avoid, right, the nth one to avoid the nth element of E, and we also want the intersection with E to be non-empty. So clearly D1's intersection with E is non-empty because x2 is in it. So clearly x1 is not in D1, and D1 intersects with E is non-empty since x2 is in D1. Okay, so far so good. Okay, and so to center ourselves and figure out how to proceed, so we'll just same picture again. So we have x1, x2. We've created this ball around x2 here. And now I want to create my second ball inside of the first one. So this is D1 here. I want to create a second ball inside of this first one, which avoids x2 and which also still contains elements of the set E, right? So this is where we use the perfectness of x2. So if we look at the open ball of this radius here, right? So the sort of the interior of D1, we know that there has to be points of E inside of here that aren't x2, right? Because x2 is not an isolated point. There has to be some point that's not x2 within E inside this ball, the interior of the ball. So there's going to be some xi, say, in there. And so what we want to do is just, I mean, it's clear that we should be able to do this. We just want to put some closed ball around xi, right? That's inside of D1 and that avoids x2. So let's start writing this down. So because E is perfect, there is an xi in the interior of D1. Okay, so that would just be the open ball, so with the closure removed here. Okay, so there is an xi in the interior of D1, which is not x2. Okay, so an xi in there different from x2. So of course x2 is in here, but that's not what we're talking about. So different from x2. And then all we want to do is just say that we can put a closed ball around this, which avoids x2 and stays in the ball D1. And so that's going to follow from a general lemma. So the general lemma is just going to, so it'll be useful because we'll have to keep going with this type of argument to keep generating our dn's. So basically the lemma is going to say that if we have a closed ball and we have 2 points that are different in the ball, so if we have, say, x and y in the ball that are different, then I can always put a closed ball around y, which avoids x and stays inside the ball. Okay, so we're going to use a lemma here. So what we do is we claim we can construct D2, which is a closed ball. Well, let's say, so we can construct a closed ball of finite radius. So I don't know why I keep saying finite, a positive radius. Around xi. Well, let me say a closed ball of positive radius, say D2, around xi, such that D2 is contained in D1 and x2 is not in D2. So this follows from the next lemma. So we have a lemma embedded in our proof here. So let's say if so suppose that let's say y let's say y and z are in a ball of radius r around x, and y is not equal to z. Right, because this is what we have in our situation up here. We have xi and x2. They're in the interior of the ball, so that's why the ball is open here and not closed. So we have two things in the interior of the ball. They're not equal, and what we want to do is put a closed ball around one of them that avoids the other one. So then there's an epsilon such that the ball of radius epsilon around z, the closed ball, is contained in the original ball, and y is not in that closed ball. Okay, so here's the proof of the lemma. So it's pretty simple. We just draw a picture. So here's x. We have a ball of radius r around x, open ball. We have y and z in the ball. And we just want to make our epsilon, put a ball around z small enough so that it fits in this ball and avoids y. So we want epsilon to be less than, let's say, half the distance between z and y. And so that should put y on the outside of that little ball. And also we just need epsilon to be smaller than this distance here. So if we look at this distance here, that is just, right, so this full distance along here is r, so, and the rest of it is x minus z, right? So we have x minus z here, the full thing is r, so that remainder there is going to be r minus the length of x minus z. So if we set epsilon to be the minimum of, we'll take r minus length of x minus z over 2. Okay, so to keep that closed ball squarely inside the open ball. And we'll also take it to be less than or equal to the length of y minus z over 2. Okay, so we claim that this epsilon works. So we claim this epsilon does the job. So clearly epsilon is greater than 0. Right, the distance between x and z, z is in this open ball, right? So that this is less than r. This is greater than 0. Y is not equal to z, so this is greater than 0. Does the job. So we claim this does, or works. So clearly y is not in the epsilon ball around z, the closed epsilon ball around z, since the distance between y and z, well, the distance between y and z, we know that's, so epsilon is less than or equal to the distance from y to z over 2. So 2 epsilon is less than or equal to the distance from y to z. So in other words, distance from y to z is greater than or equal to 2 epsilon, which is greater than epsilon. Right, so the distance from y to z can't be less than or equal to epsilon because it's explicitly greater than it. So now let's say w be in the closed ball of radius epsilon around z. So in other words, the distance between w and z is less than or equal to epsilon. So then we just want to know that w is in the r ball around x, the open r ball. So we just want to say the distance between w and x is less than r. So then the distance from W to X, we'll just use the triangle inequality. We have the distance from W, so we know about Z, so we need to insert Z in here from the triangle inequality. So you have Z minus X. W minus Z, we're given that's less than or equal to epsilon. That's less than or equal to epsilon plus length of Z minus X. And what do we know about epsilon? It's less than or equal to this. So that's less than or equal to R minus length X minus Z over 2, then plus the length of X minus Z. And so that's just R over 2 plus the length of X minus Z over 2. But Z is in this R ball around X, so this is less than R over 2 plus R over 2, which is equal to R. So, indeed, W is in the ball of radius R around X. And it follows then that the epsilon ball around Z, closed one, is contained in this open R ball around X. So that completes the proof of the lemma. Okay, so what this gives us then is our ball. So returning to the proof of the theorem, we now have D2, this closed ball, contained in D1, such that X2 is not in D2, and Xi is the center point of D2. So in particular, D2 intersect E is not empty. Okay, so that kind of completes the base case of an induction. So what we'll do now is, so now suppose that D1 contains D2, contains, etc., up to Dn, such that Xi is not in Di, and each Di is centered on a point of E, so that, in particular, Di intersect E is non-empty. Okay, so it's just convenient. I mean, really, ultimately, all we need is this, but it's convenient in our construction to have the intersection actually occurring at the center of the disk. Okay, which we've maintained in the first two constructions, so we'll just see how we can maintain that in general. Okay, so now we want to show that we can construct, so we'll show we can extend the chain of disks to Dn plus 1. Okay, so supposing, so if xn plus 1 is not in Dn, then we can just set Dn plus 1 to be equal to Dn. We can just set dn plus 1 to be equal to dn. Okay, that's clear. All right. Then we'd have xn plus 1 not in dn plus 1, and dn plus 1 would still be centered on a point of E, right, and we'd still have this, we'd still have dn plus 1 contained in dn. Okay, so suppose that xn plus 1 is contained in dn. And there's going to be two cases. So if xn plus 1 is not the center point, so there'll be two cases. So consider two cases. Xn plus 1 is not the center point and it is. So let's let y in E denote the center of dn. So in the first case, and if xn plus 1 is not the center point of this disk, we can just set dn plus 1 to be equal to basically just keep the same center, right? So if xn plus 1 is, I guess, I don't know, it would help to maybe have a picture, right? So if y is here in the center, xn plus 1 is not y, then we can just sort of, you know, think about taking this disk and just shrinking it to be small enough. So we can, you know, shrink it to be half the distance of between y and xn plus 1. Okay, so that would clearly work in that case. So we'll set the n plus 1 disk to be, we'll take a closed ball of radius y minus xn plus 1 over 2 around y. Right, so a closure, so it's closed. We can just set that, which clearly satisfies the conditions. In the latter case, we have that xn plus 1 equals y. So xn plus 1 is at the center of this of the disk dn. And so what we have, so dn, this is the closed ball of some radius r around xn plus 1 for some r greater than 0. Well, because E is perfect, there's got to be some other element of E in the open ball of radius r around xn plus 1. So there is I'll just say there is z in E such that z is not xn plus 1 and z is in the open ball of radius r around xn plus 1. Well, now we have 2 distinct points in an open ball, so I can find a closed ball inside this open ball which avoids xn plus 1. So by the lemma, there is some closed ball, so dn plus 1, a closed ball of positive radius around z, which excludes xn plus 1 and is contained in this ball. So dn plus 1 is contained in dn, xn plus 1 is not in dn plus 1, and dn plus 1, right, it's centered on z, and that's the point of E, is centered on a point of E. Okay, so what we've shown is, so in any case, we can construct an appropriate dn plus 1, so the proof is complete. Okay, so that was kind of a little bit of a long one, just a technical thing showing you can construct these balls, these appropriate balls, so you can make the proof that we used to show the uncountability of R work in this case. And so this shows the uncountability of the Cantor set and other, well, any perfect set. So other types of Cantor-like sets that you could construct in higher dimensions, as well as more friendly-looking sets like closed balls, closed cubes. Those are automatically uncountable by this argument as well. Okay, so we thus see that the Cantor set is uncountable. So the corollary, the Cantor set is uncountable. All right, so that basically concludes the difficult part of the discussion about the Cantor set. So we pretty rigorously showed that the Cantor set is uncountable, and we showed that it's a non-empty compact set, right? And we also argued properties about limit points. Every point of the Cantor set is a limit point of the Cantor set, and that the Cantor set has no interior. So we talked about many of the topological properties of the Cantor set. But now I want to shift course and just talk not very rigorously about a different aspect of the Cantor set. So something about the Cantor set that leads in a totally different direction. And so this is not really even a proper introduction. It's kind of just to whet your appetite for something different. So we saw that the Cantor set has a cardinality which would be the same as the cardinality of an interval, right? Uncountably many elements. But the length of the Cantor set, if we were to assign such a sensible notion, should probably be 0. So the Cantor set has a sort of more like a point in this sense, right? Something of length 0. And one way to make the tension between these two pictures, so the Cantor set being like both simultaneously like an interval and like a point, is in the notion of the dimension of the Cantor set. So there's a way to talk about the dimension of the Cantor set, and it turns out that this dimension is between 0 and 1. Okay, so this sort of makes quantitative this tension between the fact that the Cantor set seems in some sense like an interval, but then in other senses like a point. And so the first observation that leads in this direction is to observe that the Cantor set has a kind of self-similarity about it. So the Cantor set is equal to 1/3 times the Cantor set. So you take everything in the Cantor set and scale it by 1/3, and then union with this will look familiar, 2/3 plus 1/3 times the Cantor set, then you just get the Cantor set back. So in other words, the Cantor set is sort of two copies of itself scaled by 1/3. So if you scale the Cantor set by 1/3, right, you need that one scaled copy, and then you take another one and you translate it by 2/3, and then you get the Cantor set back. Okay, so in other words, the Cantor set is two copies that are a third as big. Okay, so if you take the Cantor set, you scale it by a third, two of those copies will then cover the original set. So we can prove this. So sort of formally this follows from the fact that, right, our Cantor set was defined by these intersected finite unions of intervals, right? So we had these Cn plus 1 is 1/3 Cn union 2/3 plus 1/3 Cn by letting n go to infinity. Okay, so if you sort of think of C in some sense as a limit of these sets, right, then you kind of have, just letting n go to infinity, you're going to have C is equal to, right, the Cn's turn into C. But of course, this doesn't really literally make any sense, so we need a more rigorous argument. Okay, so it turns out to be kind of difficult. So, I mean, a natural thing to do to prove this would be to use the fact that, well, C is an intersection of all of these things, right? So C is the intersection of these Cn's. And then to try to use this equation, right, to get something, right, to turn these Cn's into, Cn minus 1s, and then you have intersections of unions. But it turns out those intersections of unions don't really work so well together if you think about it carefully. So actually that turns out to not be the best way to go about it, though you could make it work. But it actually follows easier from something that we've already done. So where we're going to start is, so the first step is to show that the set of endpoints is to show that if we look at the set of endpoints, that satisfies the same equation. And then we'll just end up using the fact that C is the closure of the set of endpoints. That'll carry the day. So to see this, so this is actually simple. So C here is an intersection of these C's, which the intersection doesn't work so well with the union. But the E's, remember, were defined. E itself is a union of all of the E's. So E is a union from n equals 0 to infinity of En. And actually, we can drop E0. So E0 is just the endpoint of C0. So that's the set 0, 1. But E0 is contained in all of the subsequent sets, so it doesn't matter. We can just drop that. This is n equals 1 to infinity of En. And each En here is defined in terms of the one before it. That's why we had to kick out E0, because E0 is not defined in terms of the one before it. So this is the union from n equals 1 to infinity of 1/3 En minus 1 union 2/3 plus 1/3 En minus 1. And then what we can do, I guess I'll just make sure I'm clear about this. If we shift the index down in the union, that'll shift it back up, so we don't have the n minus 1s inside there. And then this is just a big right? So we just have union and union, right? So union of union is just a big union. We can union however we would like. So this is going to be the union n equals 0 to infinity of the 1/3 ENs union the union of the 2/3 plus 1/3 ENs and that's easily seen to be just 1/3 times the, and so you can basically pull those arithmetic operations out. That's just simple. So union 2/3 plus 1/3 the union En, and that's just 1/3 E union 2/3 plus 1/3 E. Okay, so basically, yeah, this one's relatively straightforward. And then it then follows that, well, C being the closure of E, well, E I can write as 1/3 E union 2/3 plus 1/3 E, the closure of that union. And here's a little exercise for you. The closure of a union is the union of the closures. So this is equal to 1/3 E closure union 2/3 plus 1/3 E closure. And we can just, that closure will pass by these arithmetic operations by the algebraic limit theorem. So this is just 1/3 E closure union 2/3 plus 1/3 E closure. And that's 1/3 C union 2/3 plus 1/3 C. By using the fact that A union B closure is A closure union B closure. That's an exercise. And the algebraic limit theorem. Okay, so that concludes the proof. Okay, so in other words, just to restate the conclusion of this again, so the moral of this we're supposed to take away. So if we scale C down by a factor of 3, or I guess to be more precise, a factor of 1/3, we need only 2 copies of C of this scaling, of this scaled down set to cover the original. So contrast this with, contrast with an interval. So if you take an interval, so you scale 0, 1 by 1/3, right? Then what you get is 0, 1/3, and we need 3 copies of that to get the original 0, 1 back. So we need 3 copies of 0, 1/3 to cover 0, 1. So 2 do not suffice. So essentially, sort of intuitively where this is going is that this means the dimension of 0, 1. This indicates how that the dimension of 0, 1 is bigger than the dimension of C. So you might also compare with with a point. So if you take a single point and you scale it by by some factor, by 1/3, then well, you still just have a single point. So you only need one copy, right? So the dimension of a point is small; it's 0. You only need a single copy after you do the scaling to cover. But with the with an interval, you scale by this 1/3. You need 3 copies to cover the original. So you can also contrast. So it's revealing to look at this in higher dimensions. So in higher dimensions, or let's say in Rn, so consider the unit cube, the product of the closed interval 0, 1 with itself n times. So if we scale all of Rn by a factor of 3, or well, I guess 1/3 to be precise, we get, or our cube, the cube becomes zero 1/3 to the n. And so what we need, we need 3 to the n copies of this to cover all of the originals, so to cover 0, 1 to the n. Right, because 0, 1 to the n, 0, 1 is 0 1/3 union 1/3 2/3 union 2/3 1. And to locate a point in 0, 1 to the n, right, you have to say where you are in each one of these intervals, and so that it involves 3 choices for each interval. Right, so for each interval here, I make one of 3 choices, and I have to do that n times. So that's 3 to the n choices. So hopefully that makes sense. And just you can just draw a picture in the case for n is 2 and 3 to see that this makes sense. Right, and so you see how. So notice the dimension n comes out in the exponent here. Or I guess I should say in the exponent of. So basically the idea of dimension is if you so scale by, let's say, 1/s, then you record, so the number of copies you need to cover the original. Let's say that's m, then the dimension that's going to be d equals, so in this example up here, this n, we can get that n by taking the log of the number of copies, or let's just say ln. It doesn't matter the base, but anyway, take the ln, then you get n times ln of 3, and then you want to divide by the ln of 1 over this scaling factor. So what we have here is ln of m over ln of s. Okay, so let me okay, so hopefully you see how that that concurs with the situation in Rn for familiar examples like a cube. And let's see what that. So what does this translate to for the Cantor set? So for the Cantor set, so when we scale, so we scale by a factor of 1/3. So the number of copies we need is equal to 2. And so the dimension, according to this formula, should be ln of the number of copies over ln of the inverse of that scale factor, so ln 3. And of course, this is a number less than 1. Right? So this is between 0 and 1 strictly. Okay, so kind of a funny idea. Definitely not. Well, first of all, this is not even really rigorous. I kind of haven't. I don't know. Kind of only indicated the sort of basic idea of dimension. But in fact, one can make this whole thing rigorous and show that this is the correct dimension of the Cantor set. So this is one sense in which the Cantor set falls sort of strictly between a point and an interval. So as a cardinality, it has the same cardinality as the interval. Its size or its length is comparable to a point, so it's more like dimension 0. But the actual dimension, if you work through all of the definitions, you can show that it really does come out to be this number, ln of 2 over ln of 3. So it might be kind of useful to compare. So if we compare comparison of the rational numbers and the Cantor set. So in terms of cardinality, just purely set theory-wise, the rationals are smaller than the Cantor set, right? Countable versus uncountable. Whereas in terms of what's called measure theory, and this would be the length or the size, sort of intuitively, they're actually equal. So the rational numbers and the Cantor set both have a sort of size of 0 inside the real numbers. Whereas as far as dimension goes, right, the rationals are going to be very much like a line. So if you take, say, the rationals in 0, 1, and you scale that by 1/3, right, you're going to get all of the rationals in the interval from 0 to 1/3, and then you just need to shift that 3 times to get the original back. And so the dimension of Q is going to be greater than the Cantor set C. So we see we kind of have these 3 measures of the size of sets. One, so this is sort of set theory, right, just purely set theory. And then we have measure theoretic and then dimension theoretic. And these notions are totally different, right? So we get 3 different answers here, right? So we take these 2 sets. In one sense, one is smaller, and Q is smaller than C. In another, they're equal, and in the other, the inequality. In the third, the inequality is from the first is totally reversed. So this gives you maybe a broader standpoint from which to appreciate, the sort of complexity of the real numbers and the subsets of the real numbers and the diverse number of ways you can think about and conceptualize and quantify various notions of the size of subsets of the real numbers. And so basically, the reals are pretty weird, and there's plenty of phenomena that might be worth studying, but this is only the bare minimum. I can only indicate future directions you might take your study in terms of studying measure theory in the real numbers, measure theory more generally, and dimension theory as well. All right, so that's going to do it for this lecture. Hope you enjoyed.